Okay, let us begin. Today we have a special meeting in our seminar. This is the second lecture dedicated to the memory of Olga Ladyzhenskaya. This lecture was organized 2 years ago when Olga Alexandrovna became her centenary. And the last year, the first Ladyzhenskaya lecturer was Professor Ari Laptev, and our today lecturer is Professor Susanna Terracini. She is a full professor at the Department of Mathematics in the University of Torino, and she is an associate member of the Belgian Royal Academy and a corresponding member of the Istituto Lombardo Accademia di Scienze e Lettere, and she was awarded several mathematical prizes, and for 4 years she served as the convener of the Association European Women in Mathematics. Yeah. So, Susanna, you can share your screen.
Okay. Okay.
Yeah. Maybe a full screen.
Is it
Yeah.
okay like this?
Yeah. Perfetta.
Okay. So I can start?
Yeah.
Okay, so first I would like to warmly thank the organizers of this memorial lecture for Olga Ladyzhenskaya. I'm very honored and proud to be here today. And I also chose a topic that I hope would be of interest for Olga, because basically is a matter of Schauder estimates, and as we all know, she was a great master of Schauder estimates for mainly parabolic, but not only equation. And so I'm very happy. I dedicate to her this talk, and I'm really extremely honored to be here today to celebrate this gigantic star in mathematics, even though I was not lucky enough to meet her in person. Okay, so what I'm going to talk about today are boundary Harnack principles and degenerate equations on singular sets. Okay, and my talk is based on 4 papers. 2 are published already. One is available on the archive and accepted for publication on the Archive for Rational Mechanics and Analysis. And the third is actually going to be posted on the archive in a few days. We are just finishing it. Okay, so let me start with very basic thing that everyone knows. The elliptic PDEs appears everywhere in mathematics, in natural and social phenomena where there is some spatial diffusion or vibration are involved, and we are on a stationary, we are dealing with stationary or stationary waves solution. And so we will consider elliptic operator in divergent form. The matrix A will always be continuous, symmetric, and satisfying an uniform ellipticity condition. So this means that as a quadratic form, the smallest and highest eigenvalues are somehow bounded on the domain, bounded below and above on the domain. In general, one could think of more general elliptic operators involving also a first order, not only a divergence forms type leading term, but also lower order terms like drifts or potential. But in general, I will try to avoid in this talk, but they could be included, of course. What we mean by a solution of such an equation, we intend a solution in the variational sense or weak sense. So we take test functions in the energy space, if we like, in the space of C infinity compactly supported function with a finite energy, and we assume that the equation is satisfied in a weak sense. Okay, and then as everyone knows, while the weakening of the notion of solution has the advantage of making easier to prove the existence, then this advantage has to be paid with the duty of proving some regularity theory. And in particular, will be mainly concerned in this talk to gain the C1 or C1 alpha regularity, maybe even more if we are lucky. Okay, so let me make a little digression about harmonic functions. Everyone here knows what a harmonic function is. Is the case when the matrix of coefficient is constant or the identity. And we have many harmonic functions. We have, for example, polynomials of any possible degree. We may have harmonic functions on cones, which in polar coordinates are in 2 dimensions, have this form. Well, we all know that harmonic functions are analytic, and they actually enjoy the mean value property, and they are analytic. And there is one rephrasing of the classical Liouville theorem, which is actually in the root of the regularity theory, which is the following statement. If you take a harmonic function, which is entire, so it's defined everywhere in Rn, and this grows less than linearly at infinity, then it is necessarily constant. And as we agree that in every talk there should be a proof, let me give a very short proof of this statement. We use the Poisson representation formula, and so we can write in a certain ball of Rn the value of the solution of the harmonic function as a boundary integral involving the values of the function on the boundary. Then we can differentiate with respect to x, and we obtain a similar expression for the gradient of u. And now, if we have some information on the growth of u on balls of radius r, we derive an expression for the gradient of u at the center of the ball, which is of this type. So if alpha is the growth of the maximal growth of u at infinity, then here there is a modulus lacking here. Then when r goes to infinity, we obtain that the gradient of u has to vanish at x0, but x0 was any point, so the function u must be constant. And well, if you join this theorem with a scaling argument, and then this is a key to prove Hölder continuity of solutions to elliptic equations with continuous coefficients. And this means that we can bound the Hölder seminar with a constant. The constant depends mainly on the dimension, on the domain, and on the alpha, the exponent alpha in the Hölder continuity. Okay. And well, of course, we can iterate this argument and then find a higher order regularity for the solution. And mainly, this is related, or may be related, with the following corollary to the Liouville theorem I stated before, that say, okay, if I have an harmonic function in Rn, which has an algebraic growth, so grows at infinity like a power, not more than a power, then this is a polynomial. Okay. Well, this is one side of the Harnack inequality in general, and this, if you take the Poisson formula I stated before, this is very simple to be checked, that if we have a positive and non-negative solution, sorry, this is lacking, non-negative solutions, solution in an open set omega, then in all compactly contained open sets omega, the supremum of u is smaller than a constant that which do not depend on u, or times the infimum of u on the same set. Okay, and this can be also derived by the Liouville theorem, and vice versa. They are actually somehow equivalent. Now we go to some other classical results that involves now not all the solutions to an elliptic equation, but the ratio. So we take two functions, two solutions, v and u, to the same equation, and we assume that they both vanish on a certain portion of the boundary, and one of them, the denominator, is positive inside. Well, in these circumstances, sorry, the ratio of the two solutions is not only bounded, but is an Hölder continuous function. This happens under very mild regularity assumptions on the boundary, or being Lipschitz, for example, or even less than Lipschitz. When the boundary, this is a very useful information which has been used many times, notably in free boundary and nodal problems, for example, by the author that I listed here. And when the boundary is more regular, then the ratio is also more regular. Okay, so one can bound not only the ratio, but the derivatives of the ratio shows at the boundary. So we have, I'm stating here, a classical theorem by Jerison and Koenig in 1982. When omega is a non-tangentially accessible domain, I will try to explain with a picture in a moment what it means, and we have two harmonic functions on the same domain in a ball, which both vanish on the same portion of the boundary, and the denominator u is positive inside, then the ratio is Hölder continuous of some order alpha, of some exponent alpha, and in particular the the ratio has a trace on the boundary, and this trace is Hölder continuous. Okay, here is a pictorial description of a Lipschitz boundary here on the left, and on an NTA domain for the specialists who already know what any NTA means. Okay, now, so the idea is to look at ratios of solutions to elliptic equations, and more recently, the theory, these principles, the boundary Harnack principles, have started being extended to boundary Harnack principle on nodal domains. What does it mean? It means that if we have a, let's say, harmonic function U, which has a non-trivial nodal set, Z of U, okay, and we take another function, a harmonic function V, which has the property of annihilating when U does, okay, then we can seek some comparison principle between U and V, which are expressed in terms of local Hölder estimates for the ratio and possibly for its derivative. And there is a very important breakthrough in this direction that has been given by Logunov and Malinnikova in papers published in 2015, and then a second one in 2016. And well, in the first paper, they showed that the quotient V over U is an analytic function. When, well, in the case of the Laplacian, but let's say that the argument in general works for real analytic operators. In this case, each V and U is an analytic function. In particular, they do have expansions at any order. And then the point is it's not so easy, but is to compare the expansions of V of U, which are harmonic polynomials. And so the theorem is based upon the following result, which guarantees that the quotient of two harmonic polynomials sharing the same zero set is also a polynomial. This is a absolutely non-trivial division lemma by Murdoch in 1963 that says that if you have one harmonic polynomial and P is another polynomial, not necessarily harmonic, that share with Q the same zero set, or it includes the zero set of P includes that of Q, then Q divides P. So P is the product of Q times some other polynomial R. This is absolutely non-trivial, of course, because in general, for general polynomial, this is not true. Now, what is the relation of this with degenerate equations? Well, if you take U and V, which are both solution of an elliptic equation, and we take the ratio, then the ratio solves an equation, another elliptic equation, but with some weight, and the weight is just the square of the denominator. Okay, and well, what is bad is that even in the simplest case, for example, when U is a linear equation, so the zero set of U is just a hyperplane. So the most possible simple structure, this equation is too much degenerate at the characteristic hyperplane. And this is the reason why it was discarded and never used in the literature. Well, for example, it does not, this weight do not belong to the class of good weights for the expert, the Mukhenaupt class, for which solutions are known to be Hölder continuous. So our point of view is to try to attack the problem, the Harnack inequalities, Harnack boundary principles by means through the study of this degenerate equation. Okay, and so now we start with the simplest case of a elliptic equation, which where there is a weight appearing, and this weight is a power of a defining function rho, which vanish at a very regular set. This means a hypersurface gamma contained in Rn, and we seek a local Schauder estimate up to gamma for solution of this singular or degenerate elliptic equation, singular or degenerate, depending whether the exponent A is positive or negative. And the exponent will be always taken larger than -1 in order to ensure the local integrability of rho to the A. Okay, but the hypersurface can be either contained in the boundary of omega or in its interior. Okay, in the first case, we write omega plus to emphasize that omega is essentially on one side of gamma, and in the second, we drop the plus from omega to emphasize the fact that gamma lies also inside omega. Okay, what a solution is, we must think of a solution in the energy sense. We have a weighted Sobolev space, okay, where the weight also appear as in the definition of the space and in the scalar product. And so we think that a solution satisfies this is a solution in the weak sense, and so basically they are critical point of the energy functional on H1A. Actually, this definition must be slightly changed when A is less than 1, but I will not say more about this. Okay, now, in fact, this degenerate or a singular equation appeared in many problems in PDEs. For example, fractional powers of elliptic equations, edge operator, and in the study of geometric PDEs in Riemannian manifolds with the singular or degenerate boundaries. Okay. Now, excuse me. Okay. Now, when A is large, is small, is between -1 and 1, then elements of the energy space have a trace on gamma. Whereas in the super degenerate case, when A is larger or equal than 1, the space of solution of function which are, sorry, here there is a minus gamma lacking. The set of function which are 0 on gamma is dense in H1A, and so traces are not meaningful. And well, about the boundary condition, we are assuming the natural boundary condition, and you see appearing the weight also in the boundary condition. So this is not it's not a true, let's say, it's a true boundary Neumann boundary condition, but in a weak sense in general. Okay, so in fact, in the super degenerate case, which is in fact our goal, because we are interested in the case A equal 2, all solutions in the belonging to the energy space is a solution in the energy sense. Okay, so this means that the boundary condition is automatically satisfied. Okay, and it is also important noticing that in general, when A is larger or equal than 1, energy solution can be very well discontinuous at gamma. Okay, so now we consider the easiest case. The easiest case for the geometry of the hypersurface gamma, which is the case when it is an hyperplane. In this case, this may be a slightly confusing. The dimension will be n+1 to say that x is the variable on the hypersurface and y is the n+1th variable. And in this case, we can always reduce our study to the case when the defining function rho is just the modulus of y. Okay, so the distance to the hyperplane. So we consider this type of equations, and in this type of equations, we have that. Okay, so we take a matrix A, continuous, symmetric, and uniformly elliptic, and we denote by sigma the characteristic manifold. Okay, now let me just recall the very classical results without weights. The building blocks of the regularity theory for elliptic equation without any weight in the uniformly elliptic case. We know that if we by the Georgi-Nash-Moser theorem, that every solution of the homogeneous equation is in fact Elder continuous, and the exponent alpha depends only on the parameters of the ellipticity and other parameters. In general, here we seek interior estimates. Okay, so we go from the ball B1 to a smaller ball. And when the matrix A is continuous, we can take any exponent alpha. And then if we add to the equation some right-hand side, some non-homogeneous terms, so if the equation is not homogeneous, so we have a right-hand side, then we have similar estimates of Elder continuity, which also involve f, small f, and the field capital F. And these estimates also depend on the dimension in a certain very well-known way. Okay, so, and when we go to matrices which are of class C0 alpha, so these are the classical Schauder estimates for the same type of non-homogeneous equation, we have C1 alpha estimates for the solution with this type of bounds, which depend again on the dimension and on the exponent alpha. Okay. Now, in our case, this classical theory cannot be applied because of the presence of this weight. And the presence of this weight may, in fact, affect the regularity. Let us consider a special case when the matrix is the identity and A is between -1 and 1. Then we have this type of solution. Okay. This type of solution is, well, in the case when A is less than 1, is in fact only larger than 0, is only Elder continuous. Okay. Let me say that this function will not solve our problem because will not satisfy the correct boundary condition at sigma. But this case is particular because false in a theoretical framework which has been developed in the early 80s, starting from seminal papers by Fabes, Koenig, and Serapioni, who identify a special class of weights, which are called Muckenhaupt weights, which in fact may be inserted in the equation by keeping some nice property for all solutions. In particular, the class of A2 weights, which in fact correspond to the case when our exponent is between -1 and 1. In this case, we have the validity of maximum principle, unique continuation principle, Harnack inequality, and eventually Hölder continuity for all energy solution. Okay, and these are the two fundamental properties of the Sobolev space, of the weighted Sobolev space associated with A2 weights. Okay, but as I said, this may be useful when the exponent A is between -1 and 1, but not when A is in the superdegenerate case. In that case, in fact, we do have solutions which are not continuous, then of course, not even, not for sure, not Hölder continuous. Okay. Now, in order to understand to obtain our C1 alpha estimates, the desired estimate for all possible values of A, our strategy consists in taking the weights, regularize them, and then obtain and look at the regularized problem where the weight is regularized on both sides and also on the boundary condition, and to derive both C0 alpha and C1 alpha estimates which are uniform with respect to the parameter epsilon. Okay. In this case, of course, these estimates will yield the same estimates for the singular or degenerated problem. But also be careful here. But also will be if we have this Neumann boundary condition, this is the conormal derivative, but the weight is a scalar. So here we can just cancel this. So this will bring, let's say, a defective Neumann boundary condition to also into the limiting problem. Okay, and now, in fact, as a first step, we succeeded with in this program, and we were able to obtain C1 Schauder estimates, also Hölder, but I want to focus on the Schauder estimate in the case which are exactly the very same Schauder estimate as the classical one, the one without the weight, once one replaces the dimension with the homogeneous dimension, which is n+1 plus a. But beside that, the estimates are exactly the same. And as I said, and they are, because they are epsilon stable, they hold for every epsilon, and they can be brought to the limit as epsilon go to 0. And also an advantage, further information we obtain from this regularization argument is the validity of a true Neumann boundary condition. Okay, so not only the gradient exists up to the boundary, but also we have this boundary condition. Okay, and if we wish to have higher order boundary condition, okay, so higher order estimate, okay, we have to assume that more regularity of the data, which the vector field F and the matrix A must be CK alpha, the small f CK minus alpha, CK minus 1, and we obtain that the solution is CK plus 1 alpha, okay, in a smaller ball. Okay, and again, we, of course, we have this pointwise estimate with pointwise Neumann condition up to the boundary. Okay, now let me say that when the exponent A is positive, we can also consider equations which have a singular right-hand side. So here we have the exponent A, and here we have A minus 1. A must be positive, otherwise this is not locally integrable. And we obtain, in fact, the same, but in the same statement as before for higher order equation, for higher order Schauder estimate. And you see that the singular part here appears in this true boundary condition at the boundary. Okay, so the strategy is the one of, as I said, of regularize, and then we make some blow-up analysis, and we end up with some function that are solve equation on the whole space or half space. And so we use the Liouville theorem that I will discuss in the end to obtain our statement. Okay, so now now we have a nice theorem. We have developed a nice theorem for the hyperplanes. Okay, and this is rather easy when we have a theorem with flat boundaries, but we can allow the coefficients to be variable. Then we can very simply flatten boundaries, and so we can apply our theorem when we have two functions u and v which solve non-homogeneous elliptic equation, and so we take the ratio w equal v over u. U is positive inside with non-negative, with non-positive, sorry, with strictly negative derivative. And then we see that the ratio v over u solves this equation with a weight u squared here, and here u. So it's 1 power less than 2. So we can apply our theory, and we obtain, in fact, let's say a boundary Harnack principle for variable coefficients elliptic equation with right-hand side, which are in fact very similar to the known ones they are the analog of the ones known for the Laplacian. Okay, So when the data are regular enough, and the boundary also is phi is the parameterization of the boundary is of class CK plus 1, then the ratio gains 1 irregularity. Well, this one is not for free, because we know that U and V, they are CK plus 1 alpha, okay? And U is 0 with non-zero derivative at the boundary, while V is also 0. In general, when you take the ratio, you will lose 1 in degree of differentiability, no? Of course, because you are kind of differentiating, okay? But so this theorem says that you are not losing this one. This one will not be lost. The blue, so this is the general estimates, and for those who are acquainted with higher order boundary principles as in the classical literature about the blue one is the usual way. So in general, we can take the ratio at one point, provided in this case, both U and V are positive. Okay, now we go. So now we were able to deal up to now with the variable coefficients, but with regular non-degenerate hypersurface gamma. So now we try to have a nodal set for the weight, which is more complicated than one manifold. Okay, and now we go back with, so what we actually would like to do is to extend the theorem by Logunov and Malinnikova from the analytic setting into, let's say, for the class of coefficients which are less than analytic. Okay, and okay, now we want to do this again by looking at the degenerate equation. Okay, now we have to be a little careful. We consider we can divide the zero set of U into two parts. The regular part, where U is the gradient of U is non-zero, and this is of course made of C1 alpha, CK alpha, depending on the degree of differentiability of U hypersurfaces. But there might be also a singular part, that is the part where the gradient of U is 0. Okay, so the regular part is locally an n-1 dimensional hypersurface of class C1 alpha, and the singular part is known to have a small Hauser dimension, at most n-2. Okay, so now, we start with one solution, which is a C1 alpha function, maybe more, of an elliptic equation with coefficients which are, let's say, Lipschitz. And now we take a second equation, a second solution, which has the property of being 0 whenever the first one is. Okay. Now, well, of course, so as I said, if we try to get information from the equation, from the degenerate equation solved by the ratio, we are very easily stuck because, as I said, the solution of this equation need not even to be continuous. Okay, but let's say that we assume W to be continuous at the zero set of U. We may assume it. Well, first, when we go across the regular regular part of the nodal set, so just forget for a moment of the complications due to the presence of a singular part of the nodal set. We stay for a moment, still stay on the regular part. So when we assume the solution W to be continuous, then we have very nice Schauder type estimates. So when A is CK alpha, and the ratio is whenever the ratio is continuous, then it is CK plus 1 alpha. Okay, so this is the first advancement. Now, before going to the case of singular of a singular nodal set, let me spend a few words about the Liouville theorems, which are at the basis of the theorem of the theory for the smooth nodal set. Okay, here we have the first Liouville theorem I want to present is the following. This is a regularized weight. So this may be when epsilon is equal to 0 is modulus of y to the alpha. Y is positive in this case. When epsilon is 1 is square root of 1 plus y squared to the power a. And okay, so the point is that if we take a solution of this equation with Neumann with a Neumann boundary solution condition, and we know that the solution grows less than linearly, then it is constant. And as I said, this is good for getting Hölder continuity of solutions. And if we assume now that the gradient of W grows less than linearly, then W is a linear function and depends on X only. Okay, now, so this was the underlying, the Liouville theorem underlying the regularity at a smooth part of the bound of the zero set. Now, let's look at the papers, the results by Logunov and Malinikova, and as I said, they use as a key result for them this division lemma. And the division lemma I already stated at the beginning can be reformulated as a Liouville theorem for harmonic functions in the following way. We consider a harmonic polynomial and an entire harmonic function with the property that whenever V is 0, also U is 0. Well, otherwise the ratio will not be bounded. Okay. Then assume that the ratio V over U grows less than some power, any power. Then it is a polynomial with a degree at most that power. Okay. Okay, so now, of course, we can restate this in terms of the weighted equation, saying, okay, when we have a harmonic polynomial and an entire continuous solution of this equation, okay, and we know that this this solution W is continuous, and it grows less than some power of x of z at infinity, then W is a polynomial. Okay, and with this Liouville type theorem, we can extend, for example, estimates Harnack type of inequalities for the ratio in general nodal domains, extending some result by Lin and Lee. Okay, now let me also make some remarks about the properties of compactness that we wish to apply to the weight U. Now, for those who are a bit acquainted with minimal surfaces, but also with equations with a certain approach to elliptic equations, it will not be a surprise to see here the Almgren frequency function, this associated to our equation. Here the ball is not the Euclidean ball, is the geodesic ball associated with the metric. And it is known that when A is Lipschitz, then this function is absolutely continuous with respect to R. And in fact, there exists a constant for which e to the CR n is monotone. And then it may be reasonable to consider functions U, which are not only solution of the equation, but are normalized in L2 norm, and they have a bounded frequency. Okay, and then we have this property which says, okay, if we bound, so now take two functions U and V, which are both solution of the same equation, and they are in the same class, then the ratio is bounded, and the ratio is bounded in Hölder spaces, and the constant does depend only on the class S and 0. This means on the dimension, the ellipticity parameters, and the Lipschitz constant of the equation of the coefficients, and the bound on the Almgren functions. Okay, so here the point is not only they are bounded, but they are uniformly bounded. Okay, now let's try to obtain some higher order estimates, and which also should be the uniform in this class. And we succeeded in doing this only in 2 dimensions. Okay, in 2 dimensions, we consider a pair of functions. Sorry, this is in the same class S, with the same properties as before, that when V vanishes, also when U vanishes, also V does, then the ratio is actually C1 alpha function with an alpha that depends also on the bound of the Almgren function. Actually, very recently in this new paper, we were able to remove this bound and say that they will be C1 alpha for every alpha. Okay, so now let's go to the case. So now we have our strategy for attacking this problem was, as I said before, that of considering the equation with a weight, the weighted equation, even though it is super degenerate, okay? And when we are able to do this with the power 2 for the ratio of 2 solution has here the power 2, it is very natural to go and look at the same equation with a different power. Why this makes sense? This is an interesting equation because it is somehow invariant and under equivariant with respect to conformal transformation. Okay, and now again we see Schauder and Schauder estimate for W, which are uniform with respect to the class, uniformity class, as I said before, where there is a bound on the Angren frequency. And finally, we succeeded at least in 2 dimensions, okay, in obtaining both Schauder and Schauder estimates, which are uniform with respect to the class omega. So these are exactly like Schauder ones. These are a priori estimates. But when one has a priori estimates and is able to cook up, and in this case, this is not at all easy, and some approximating procedure, then the a priori estimate will become a posteriori estimates. Okay, and what is, I'm almost finished, sorry, my time is over. What is at the basis of this equation is another Liouville theorem, which I think is also has an independent interest, that says that if we have an entire, well, continuous, and let's assume that non-constant for a moment, solution to this equation is in R2, okay, and we assume that it grows less than quadratically, then U and W are both affine function with the gradient, with orthogonal gradient. This means that W is a multiple of the harmonic conjugate of U. Okay, so the final remark that when U is a harmonic polynomial and W is its harmonic conjugate, then W is actually a solution of this equation for any value of A. Okay, so this is all I wanted to share with you today. Thank you very much for your attention.
Thank you.
Well, let's thank the speaker. Yeah, and please, questions or comments? No? Well, I have a question, Susanna. When you deal with the first problem, the first problem, when the functions vanish in some given surface, yeah?
Okay.
You have Schauder estimates, but am I right that the Georgia type result is not true here?
Sorry,
The Georgia type result, so that if you have no regularity of coefficients, then nevertheless you have Schauder.
Correct, correct. In fact, we didn't do this. So, in fact, I think that a result that should be true are the George type results. So, in the case when the coefficients are only, let's say, L infinity with a bound of the ratio of the
Mhm.
of the higher and smaller
Mhm.
eigenvalues. Yeah, in fact, I think that this should be true. So that there should be older bounds for ratio for the solutions in any case. And I think that with Cristiana De Filippi at some point we wrote down a proof, but we never published because in fact we were already going in other direction. Yeah, it is possible to do. Maybe some young person could
Okay.
could try, and could be, I think it would be interesting to have a proof written. I believe it's true.
Okay. Yeah, and the second question is as follows. You require in some point that the denominator is not only zero at this surface, but has the non-zero normal conormal derivative. Yeah.
Okay.
Yeah. But A is in this point, A is uniformly elliptic matrix.
Correct. And also Lipschitz yeah, okay. So let me yeah, but please note that we developed the theory for smooth, let's say for smooth curved boundaries when F and G are where the V and U are solution of non-homogeneous.
I see. So if, for example, G has sign, then this normal derivative is not zero anyway.
Yeah, yeah. But otherwise, you have to have it as
Yes, surely,
yeah.
surely.
Yeah.
Okay. More questions or comments? Okay. If not, Susanna, please stop share.
Okay.
Yeah, and let's thank the speaker again.
Thank you very much. Thank you.
Yeah, and let me так, moment. And let me share my screen. As usual, the lecturer receives the diploma, and we send you electronic version, and the hard copy will be sent you in time.
In April.
Thank you.
Yes,
Okay.
I will ask you your postal address and send in April, second week.
Thank you. Thank you.
Well, so I stop sharing. Excuse me, I stop recording.